Hello guys, so I'm Ma'am Jackie and our topic for today is about special relativity. The theory of relativity is a cornerstone of modern physics. This was developed by Albert Einstein in the early 20th century. The theory consists of two major parts, the special relativity and the general relativity. The special relativity describes the behavior of objects that are moving at constant speeds relative to each other. For instance, you are inside a moving train. Relative to the environment, the train you are in is moving. Relative to the train, you are stationary. An inertial frame of reference is a coordinate system or reference frame in which the laws of physics hold true without the need for any acceleration or external forces. In other words, an inertial frame is a frame of reference that is not accelerating or rotating. Can we all observe relative motion? Yes, except for light. The Michelson-Morley experiment conducted in 1887 aimed to detect the presence of the ether. An ether is a hypothetical medium believed to be necessary for the propagation of light waves. The experiment involved splitting a beam of light and sending the resulting beams along perpendicular paths, which were then recombined. The expectation was that the motion of the Earth through the ether would cause a detectable interference pattern when the beams were recombined. However, the experiment yielded a surprising result. There is no significant interference pattern or shift in the speed of light was observed, regardless of the orientation of the apparatus or the Earth's motion. This unexpected outcome challenged the prevailing notion of the ether and played a crucial role in the development of the theory of special relativity. It provided evidence that the speed of light is constant and independent of the motion of the observer or the source of light, leading to a paradigm shift in our understanding of space, time, and the nature of light. So it can be concluded that if the light travels faster, it lowers the time. The two postulates of special relativity. The idea that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. Second, the idea that the speed of light c is a constant. It is independent of the relative motion of the source. The relativity of simultaneity. Time dilation. Time dilation is the phenomenon where two objects moving relative to each other experience different rates of time flow. Time is not absolute. In time dilation, the faster you move, the slower time passes. This is the formula for time dilation. Delta t is equal to delta t sub o over the square root of 1 minus v squared over c squared, where delta t sub 0 is the proper time interval, delta t is the dilated time interval, v is the velocity or speed, and c is the speed of light. So let us answer the problem involving time dilation. A rocket ship leaves Earth at a speed of 3/4 c. When a clock on the rocket says 1.5 hours has elapsed, it received a light signal and should send it back to Earth. According to Earth clock, when was the signal sent? Letter B, according to Earth clock, how long after the rocket left did the signal arrive back on Earth? And letter C, according to the rocket observer, how long after the rocket left did the signal arrive back on Earth? According to the Earth clock, we need to determine when the signal was sent. When the clock on the rocket says 1.5 hours have elapsed, It means that 1.5 hours of proper time have passed on the rocket. So that is the proper time interval, or the delta T sub O equals 1.5 hours, and it is in the perspective of the rocket. To find the time on Earth when the signal was sent, we need to account for the time dilation. So the formula is delta T equals delta T sub O over the square root of 1 minus V squared over C squared. So we just plug in the values and enter these values in our calculator. We can solve for delta T, and delta T is equal to 2.27 hours. So this value means that according to the Earth clock, the signal was sent back when 2.27 hours had elapsed. To find the total time it takes the signal to arrive on Earth after the rocket is launched, we must add the time that it takes the rocket to reach the point where it transmits the signal and the time that it takes the signal to get on Earth. That is, total time equals time wherein the signal arrived on rocket, denoted by TR, plus time signal arrived on Earth, that is denoted by TE. We already calculated the time wherein the signal reached the rocket, or the TR, and that is 2.27 hours. So we only need to use this result to find the total distance traveled and the corresponding time it would take a light signal to reach the Earth. The time for the light signal to travel to Earth, denoted by TE, can be solved by equating the light distance from the Earth and the rocket's distance from the Earth. Using this formula, wherein D is equal to speed times time, we can equate the distance of the light from the Earth and the distance of the rocket from the Earth. We substitute dE by the speed of light multiplied by the time the signal arrived on Earth. We also substitute dr by the speed of the rocket multiplied by the time the signal arrived on the rocket. C will cancel out, and then we plug in the values in our calculator. We can solve for the time the signal arrived on Earth, and this equals to 1.70 hours. We can already solve for the total time the light signal traveled by adding TE and TR. So total time is equal to 2.27 plus 1.70, and that is 3.97 hours. The time it takes the signal to reach the Earth in Earth's frame is 3.97 hours. With this result, we can use the time dilation formula to find the corresponding time in the rocket's frame. So we have the velocity of the rocket equals 3/4 c, and the proper time interval, or delta T sub O, is equal to 3.90 hours. That is in the perspective of the Earth. So using this formula, delta T equals delta T sub O over the square root of 1 minus V squared over C squared. Plug in the values. We have delta T equals 6 hours. Therefore, according to the rocket's clock, the signal was sent back to Earth in 6 hours. Next, we have length contraction. Length contraction is the phenomenon that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame. As an object approaches the speed of light, the object's measurement of space also changes. In length contraction, at faster speed, objects and distances appears shorter. The formula for length contraction is L equals L sub O square root of 1 minus V squared over C squared. where L sub O is the proper length, L is the contracted length, V is the velocity or speed, and C is the speed of light. To apply the length contraction formula, let's have this problem. The length of a rod at rest is 1.2 meters. What will be its length if the rod will move 1/4 the speed of light? To determine the length of the rod when it is moving at a speed of 1/4 c, we need to consider the effects of length contraction due to special relativity. So we apply the formula L equals L sub O multiplied by the square root of 1 minus V squared over C squared. The given are the proper length, which is 1.2 meters, and the velocity, which is 1/4 c. So plug in the values and enter these values in our calculator. We arrive at the answer L equals 1.16 meters. Therefore, when the rod is moving at 1/4 c, its length will appear contracted to approximately 1.16 meters as observed by an observer at rest. So we have another example. In the year 2069, Tesla wants to make a 3-meter long ultra car look like it's 1 meter for the people watching him. How fast should he have to drive this ultra car to do this? To make a 3-meter long ultra car appear as 1 meter to the observers, we can use the length contraction formula from the special relativity. L is equal to L sub O multiplied by the square root of 1 minus V squared over C squared. So we have the given. The proper length is 3 meters and our L is 1 meter. So plug in the values. We can rearrange this equation so that V is on the left side of the equation. And then simplifying it, we'll have V over C equals the square root of 1 minus 1 over 3 squared. So we can solve this already. So that is V equals 0.94 c. Or that is, the velocity is 282 times 10 raised to 6 meters per second. Therefore, Tesla would have to drive the ultra car at approximately 282 times 10 raised to 6 meters per second to make it appear as 1 meter to the people watching him. It's important to note that this velocity is extremely close to the speed of light and not achievable with the current technology. So the next topic is the relativistic velocity addition. Relativistic velocity addition, also known as Einstein velocity addition formula, is a formula used to calculate the combined velocity of two objects moving relative to each other in the theory of special relativity. Unlike classical Newtonian physics, where velocities are simply added or subtracted, special relativity introduces a different way of combining velocities that takes into account the effects of time dilation and length contraction. The relativistic velocity addition describes the velocities of an object moving at a relativistic velocity. This value can never be greater than the speed of light. The formula for relativistic velocity addition is U equals V plus U prime over 1 plus V U prime 1 plus V U prime divided by C squared. U is the velocity of an object relative to an observer. U prime is the velocity relative to the other observer. V is the velocity between two observers. And C is the speed of light. So let us solve this sample problem. Suppose a spaceship heading directly toward the Earth at half the speed of light sends a signal to the Earth on a laser-produced beam of light. Given that the light leaves the ship at speed c as observed from the ship, calculate the speed at which it approaches the Earth. How fast does a light signal approach the Earth if sent from a spaceship traveling at 0.500 c? So from the problem, the given are the velocity of the spaceship, which is 0.500 c, and the velocity of light as observed from the spaceship, which is equal to the speed of light itself. Then we identify the speed of light that is observed from the Earth. So from the equation, u equals v plus u prime divided by 1 plus v u prime over c squared. We plug in the values and then we simplify it. Simplifying it further, 1.5 and 1.5 will cancel, as well as c squared. What is left is c. So the speed of light as seen from the Earth is the same as the speed of light, which is 3 times 10 raised to 8 meters per second. So let us have another problem. Actually, this is a continuation from the previous example. Suppose the spaceship in the previous example approaches Earth at half the speed of light and shoots a canister at a speed of 0.750 c. At what velocity does an earthbound observer see the canister if it is shot directly toward the Earth? That is letter A. And for letter B, if it is shot directly away from the Earth. So from the problem, these are the given. The velocity of the spaceship, which is equal to 0.500 c, and the velocity of the canister, which is 0.750 c, and it is positive because the direction of this canister is towards the Earth. Okay, so let's have the relativistic velocity addition equation, which is u equals v plus u prime divided by 1 plus v u prime over c squared. Let us plug in the given values and then simplify it. Then let's get our calculator and solve for the velocity. And the velocity is equal to 0.909 c. This is the velocity of the canister as seen by the observer on Earth. So let's solve for letter B. Still, the unknown is the velocity of the canister as seen by an observer on Earth. It's just that the canister is directly thrown away from the Earth. Thrown directly away from the Earth. So let us use this equation and plug in the values. Take note that the sign of the velocity of the canister is negative because it is thrown away from the Earth or from the observer. And let's plug in the values. As you can see, there is a negative sign on u prime. Let's simplify this equation. And simplifying this further, we arrive at u equals negative 0.400 c. So this is the speed of the canister as seen by an observer on Earth. It has a negative sign because the direction is away from the observer. Okay guys, that's it for this lesson.